Okay, welcome to the fourth lecture on soil water constants and infiltration. Soil water constants, these are the two limits where irrigation water is decided amount of water, how much it should be given, and in this lecture we will be also dealing with the movement of water when we supply from source as micro irrigation drip emitter, and we are dealing with the what is the soil water content and the how the soil water movement it takes place when it is in the saturated condition, when it is unsaturated condition. So, depending on the aspects we the soil water content, the movement of water takes place. Now, when we say soil water constants, means soil water constants are the basis for irrigation water application. So, different terminology which are referred in soil water constant. One is saturation capacity. Saturation capacity means all the macro and micro pores are filled with water. So, here as I was referring there, the soil consists of pores, and these pores may have water, may have only air or partly filled with the air. So, if all the pores are filled with the water, means micropore, macro means the larger size pores, smaller pores. If all these are filled with the water, we call it as a saturation capacity, and this is what we are seeing here, that the soil is saturated and then water is coming out of the soil particles. The soil is at maximum water retention capacity, means water, all the pores are filled with the water. So, here soil water retention is maximum and metric suction is almost 0. The another important parameter in as a soil water constant is field capacity. Field capacity means water is held in the soil after excess water has been drained by force of gravity. So, gravitational water has been removed, means this condition attains after the gravitational water from the soil has been drained out of the soil mass. So, it depends on the type of soil. If it is a clay soil, it takes more than 48 hours, 72 hours. If it is a say very coarse soil, sandy soil, it takes only few hours, that is it could be 6 hours itself. So, that type of situation it exists depending on the soil texture. So, field capacity of what we are seeing here, the water is drained and then part of the pores are filled with the air and water. Now, there is a range for field capacity, the value is given as 0.1 to 0.33 bar. This is soil moisture tension, means it is a negative pressure. So, negative pressure available is from 0.1 to 0.33 bar. So, it will depend upon the particular texture, means if it is a fine texture soil, you are finding that it is a 0.1 and it goes up to 0.33 bar. So, it will depend upon the. So, this is a upper limit of available soil water content from irrigation point of view. Permanent wilting point, plant roots are not able to extract soil moisture, means soil moisture which is available in the soil is not adequate enough that can be withdrawal by the plant for meeting the transpiration requirement. So, means here what we are seeing, there is a moisture content available, but the air presence of air is dominating in case of permanent wilting point. So, it is the lower limit of available water, and then soil moisture tension at permanent wilting point is about 15 bar. Of course, this is the uppermost limit, but this is also in this varies with the range, means it can be lower than this 15 bar, it could be 7 bar in some soils. If it is very high, so your say coarse textured, very coarse textured soil where gravel is present, the permanent wilting point could be in the order of 7 to 10 bars, and it could be as high as 22 bars in case of clay soil. So, a general the value which is used is 15 bars per wilting point. Available water is the moisture content available between field capacity and permanent wilting point. Now, this particular diagram, it explains the available, means when we say that this is the total available water from field capacity, that is theta f c to theta w p, that is your moisture content at wilting point. So, this is the total water available, and readily available water means there is some kind of a the moisture content which is a critical moisture content, beyond which the plant does not feel any deficiency in moisture content. So, a limit is decided, this is the. So, when we are planning strategy for giving irrigation, so this theta f c, that is theta c, this particular value theta t, it is decided in such a way that it does not affect. So, when we want to partially give water content, means we are making some strategy to give deficit irrigation, in that case we are giving moisture, we are maintaining moisture content at theta t here, and this ratio of the RAW and the TAW, it gives the value the management allowable deficit. So, total available water is theta f c minus theta w p multiplied by depth of root zone, and here it is the this particular soil moisture stress coefficient. Now, this soil moisture stress coefficient is maintained to means give a specific level of stress when we have a deficit water supply, means it is not always to keep moisture content up to theta f c, that is at field capacity. One can have less than that values, maybe theta t can be maintained. So, there actually how much level of stress one can maintain, that is the, this is the meaning of K s. Now, soil water potential, it is the driving force for water to flow when soil, plant, atmosphere, it means it is the it is being maintained in the soil water potential. Water flows from higher potential to lower potential, means higher moisture content to the lower moisture content, and it indicates amount of work needed to be done to displace a unit quantity of water from a given reference point. So, if I put it, say there is a saturated soil column, from saturated soil column, because of the capillary force, the water is moving from that particular reference point to a specific point. So, that is the amount of work which has been done to displace this particle by the capillary force. Now, the total soil water potential can be explained by this equation, which is this is equal to summation of the metric potential, it is the summation of gravitational potential, it is the summation of osmotic potential, means all three potential when these are added, and this is the metric potential is because of the soil moisture content, means the amount of water which is held by the soil particles. So, metric potential, metric force comes into picture. Gravitational potential, it is the case of saturated case when the gravitational water takes place. This is the case osmotic potential when there is a concentration in the soil salt. So, I was telling you in the previous lecture about the osmotic potential or osmosis. This is the case when there is a concentration of salt in water, or it is in case of a saline soil. Now, this particular diagram it explains about the soil water potential versus volume of soil water content. So, if I look these are the three types of soil. Three types of soil: when there is a large amount of sand is present means sandy soil, when the clay, silt and the sand it is available, that is a loamy soil, and third one is your clay soil. So, what we see, the soil water potential for a given soil water potential for a given moisture content, it is in case of clay soil is higher as compared to the sandy soil. It is a simple case. If I put it here, say it is a 10 kilopascal soil water potential or soil moisture tension. If I say soil water tension is 10 kilopascal, or in tension when we are putting that is a negative part, that is a minus 10 it is written here. So, value of volumetric water content is 0.1. For the same 10 kilopascal case, the moisture content is high in case of loamy soil, and in the same soil water potential when we are maintaining in case of clay soil, the value is considerably high. So, soil water potential, how it is varying with different types of soil for the given soil moisture content, it varies with this. So, this is a important consideration one has to see when we are giving irrigation water supply. Soil water movement, it is a complex phenomena, and it variation in the state means it states the variations. It is moving in a particular direction, and then variation in the force that cause its movement. So, this is the one particular case when it is soil is saturated, means all the pores are filled with the water. When we are giving irrigation or we are supplying water, it is simply just gravitational water or free flow of water it takes place. When it is an unsaturated case, you are seeing the soil pores are partly filled with the water and partly filled with the air. This is the case of unsaturated case, and so the movement of water will be less because it is a partly filled with the air. And in case of vapor, means soil particles highly, it is the soil moisture, it is a dry soil, and when it comes with the water vapor, so movement of water does not take place, it is simply adhering with the soil particles. So, soil water movement in saturated condition, it is the hydraulic gradient which takes place from higher potential to the lower potential, and gradients when we say, so this potential or we say divided by the length of the flow path will be the gradient, and then what is the transmissive capacity of the soil, that is hydraulic conductivity. So, this can be explained by Poiseuille's equation, and which explains that rate of flow equal to P pi r to the power 4 8 L mu. So, Q is the volume of flow per unit time or rate of flow or discharge we can say, and P the pressure difference between two ends of the tube, or simply capillary tube, and let it be the soil particles where it consists of the pores. So, it forms a capillary action, and then the diameter of, here the important part is what is the diameter of this capillary tube when the water flow takes place from the soil. So, you can see how the diameter it plays role for the so it is a fourth power of the diameter which is dominating the rate of flow, and so it is inversely related to the length of flow or length of capillary tube, and then the inversely proportional to the viscosity, dynamic viscosity of the fluid or water. So, this can be given that sandy soil has got high rate of flow. It is true that diameter of the soil pores are larger as compared to the loamy soil or clay soil. So, pore size is a dominant factor when we apply Poiseuille's equation. Darcy's law is used for majority of the our case means of the flow through porous media. So, if we are considering say a soil column which is cylindrical in nature of having length L, and then we are measuring two, say there are two sides, one is the inlet end, another one is the outlet end, that is the downstream end, and then the area of cross section of flow is A. So, the difference in the head, that is H, when we are telling that H in and this is your H out. So, H in minus H out divided by L will give the hydraulic gradient. So, this is practically delta H by delta L. It is directly proportional to the discharge or rate of flow, okay, and then it is directly proportional to the area of cross section of the flow. And if I put it that rate means the flow through porous media is directly proportional to the hydraulic gradient. So, this is K sat is the proportionality constant which we call it as a saturated hydraulic conductivity. So, the expression means flow through porous media is given by Darcy's law. Darcy's law is valid only when the flow is laminar and Rayleigh's number is less than 1. In many cases, when the flow is simply it is a flow means saturated flow, literature says that for a groundwater flow the value of this Rayleigh's number is between 1 to 10. Now, in from irrigation point of view, we do not deal with the saturated flow. For groundwater flow through porous media, we deal with the saturated flow, but from irrigation point of view, it is unsaturated flow. So, water potential, that is the metric potential, is the only dominating case. The gravitational potential is does not dominate in this case, but we do take into consideration while we are when we are taking soil column, when it is in a vertical soil column. So, this Z value is considered. So, Darcy's law is applied for the when we are using the metric potential in case of horizontal flow we are considering. So, here the it is applied for unsaturated flow with some certain modification. So, the rate of flow, that is a velocity of flow, or it can be given by minus k psi, this is your psi g, delta psi g plus psi m. Now, psi g is the gravitational potential, and then this is a metric potential divided by L, that is your gradient it maintains. Now, when we consider it is unsaturated case, means hydraulic conductivity, it is a function of moisture content. Now, so this can be explained, the rate of change of soil moisture content, it is a, when we considered one dimension means one direction dimension means one dimensional case we are considering. So, let us say in x direction when we are keep putting it. So, the del by del x k theta delta psi by delta x. So, delta psi by delta x means metric this potential with respect to x. Now, this can be this particular term can be written k theta we can write. So, in the when we are considering the z direction, that is in the vertical direction when we are considering. So, rate of change of moisture content means change of moisture content with respect to time can be given by del by del z, that is in the vertical direction, downward direction. This is the diffusivity term multiplied by del theta by del z plus del k theta by del z. K theta is the hydraulic conductivity with respect to moisture content, and d is the diffusivity term, which is also a function of moisture content. Now, hydraulic conductivity is a very important point here, parameter which is playing role when we are considering flow through unsaturated or saturated column. So, it is the ability of soil to transmit when subject to hydraulic gradient. So, K will depend upon the particular type of soil texture and also water holding capacity. So, soil texture, it is a it is a function of how the pore geometry it exists, and accordingly the how much will be the water content it is available. So, that is dominating, and this is proportional hydraulic proportional it is a proportionality constant, and this particular diagram when we look that how hydraulic conductivity is changing with respect to the different types of soil and also soil water potential. So, hydraulic conductivity as the soil water potential from negative sense means negative pressure point of view, I am putting it here. So, if I put it the soil water potential point 0, 1 to 10 means this is in minus So, minus 0.01 means the moisture content is higher at 0.01 megapascal as compared to 10. So, as the moisture content or negative potential increases, hydraulic conductivity of the soil decreases exponentially, and this can be explained by this diagram. So, field capacity and wilting point, how it is varying. You can see hydraulic conductivity at the field capacity is greater as compared to the hydraulic conductivity at permanent wilting point. So, moisture content is influencing the soil hydraulic conductivity, and that it can be also seen in case of this type of two soils it is given. One is the two are the two different soils, and how important it is. The clay soil, which is a fine textured soil, and the soil water potential values are relatively higher as compared to the sandy soil. So, hydraulic conductivity, how it is decreasing with the increase in soil water potential or negative. So, a dimension of length per unit time, which is same for the means for hydraulic conductivity, it has a dimension of same as the velocity. Now, the values of K, that is a sandy soil, sandy loam soil, loamy sand soil, loamy soil, the values of K, these are the some experimental based value, these has been obtained, and for many irrigation experiment these values are used while we are deciding to give irrigation. And for when we want to find out hydraulic conductivity in laboratory condition, we use constant head permeameter method also we use variable head parameter. So, this is the diagram what you see here, this is a constant head parameter, and the right hand side the diagram B, it refers to the variable head parameter. So, as when we are bringing soil core sample, putting here undisturbed core sample, it is kept in a chamber, and then we, the particular head, constant head is maintained, and this head difference, the head at the top of the saturated soil column to the center of the outlet of this particular the cylinder. So, this we are maintaining a constant head, and this value is delta H is used to find out the head difference, and this is used to find out the hydraulic conductivity. So, a constant head gradient is maintained by adjusting the inflow. This is what you are seeing by adjusting the inflow. So, that when it becomes a constant, then only this value is used, and then we use this expression, that is K equal to volume of flow divided by time. This becomes your Q, and then that is divided by area. So, this becomes your velocity unit, and then L refers to the length of the saturated soil core sample, and T is delta H is the head difference. So, this value is used to find out the hydraulic conductivity. So, this expression is applied to obtain the hydraulic. Now, the another one is the falling head permeameter. Now, falling head permeameter is used for fine grained soil particles. Even for the laboratory purpose, any soil sample it can be brought, but it should be undisturbed soil sample, and that is brought here. So, the liquid that percolates through the saturated soil column, this is a saturated column and is kept unsteady, means here as in this case we were maintaining the constant head case, we were maintaining here this particular head is not maintained constant, we are maintaining unsteady state flow regime, as well as the head is also variable. So, not necessarily constant head is maintained during the test, and we operate the system in such a way that suppose there is a one head at particular time, we are keeping it H 1, and then we are maintaining the head H 2, and these two heads values are used to find out the hydraulic conductivity, and this is the diameter of the soil column or core, and then the tube diameter is A. So, length of tube and then area of the tube divided by area of area of the smaller tube divided by the area of the column. The T2 minus T1 means for 2 time interval when the values are taken, and then corresponding H1 and H2 is measured. So, logarithmic values of H1 and H2, and then for 2 time interval the when T1 and T2 is maintained, the hydraulic conductivity is determined, and these are the parameters that V equal to volume flow rate in time t, A is the cross sectional area, L is the length of the sample, this is the length of the sample, and H1 and H2 are the two heads at the 2 different times which is being taken, and T1 and T2 is the time interval. These are used to find out the variable parameter values for the hydraulic conductivity. Infiltration is another process which explains the entry of water into the soil, and this particular diagram, it explains the how the infiltration it takes place from the saturated media, and then the moisture content is high, you are finding, and then when the drip system, when you are operating a dripper. So, interesting part is the dripper explains the typical movement of the water, this kind of a movement of water it takes place, but the the water is moving vertically downward, and rate at which water enters is known as infiltration rate. And if experiment is continued for a longer period, so depth of water, accumulated depth of water infiltrated with time, total time in a given time is known as a accumulated depth of infiltration. And when the rate of infiltration becomes constant, after certain time steady state is reaches such, this infiltration rate is known as a basic infiltration rate. And this infiltration test is used to for the design of experiments, design of irrigation experiments, and mainly for irrigation purpose we are using the value of infiltration while we are applying sprinkler system, when we are applying the drip system, so that it does not form runoff. Application rate, it should match with the infiltration rate of the soil. Now, when we conduct the experiment and find out the infiltration depth, so what we find that with the time when you are putting it and then depth of infiltration, you are plotting cumulative depth of infiltration, you find it this kind of a graph it exists, it develops. This is known as a cumulative depth of infiltration. Now, when you take the derivative of this curve, when you are taking derivative of the curve with respect to time, this is known as infiltration rate curve. And at this particular point, when we are seeing that it has reached to the steady state or constant rate of infiltration, this is known as a basic infiltration rate. Now, infiltration rate decreases with the time. What happened when because the soil the top soil pores, it becomes saturated, moisture content has increased. So, that has caused decrease in the rate of infiltration. Now, infiltration can be measured by using single infiltrometer, single ring infiltrometer or double ring infiltrometer. And when you are, so in case of single ring infiltrometer, water, you are finding out the depth of waterfall in the cylinder. Now, it may happen beyond this depth of cylinder, water may go in the lateral direction. So, that is one limitation in case of single ring infiltrometer, but when we are using double ring infiltrometer, means the smaller cylinder is kept inside the outer cylinder. So, there are two concentric cylinder, they are of 60 centimeter in diameter, inner cylinder is 30 centimeter in diameter, and then water is being poured from the top, and then it is being allowed such that there is this outer cylinder water depth of water, it maintains a buffer zone. So, water enters vertically downward. So, this is the type of flow which we are observing here, that here it is moving lateral direction, whereas from the water level fall in the inner cylinder is measured by using the scale, by using the gauge. It could be point gauge or it could be the hook gauge, and cumulative depth of infiltration with time is being monitored, and then the cumulative depth of infiltration is plotted, and then we get this kind of a graph, means accumulated depth of infiltration with time. When it is plotted, it gets this kind of a graph, and this graph is explained by the Kostiakov's equation, which is given by z equal to a into t to the power b. And when in the infiltration rate form, when you are making the differential form of the equation z del z by z t a, then it becomes your a b t b to the power minus 1, and we can see that the this will be the infiltration rate equation. And if you want to make the means your take the logarithmic part of this equation, it becomes a linear equation, and this linear equation can be used to obtain the value of A and B. Okay, so there are other infiltration equations which are used. One is Harton's equation. These equations are superior to the Kostyakos equation, and it is used for mainly in hydrologic studies, as well as for and then the value of K as well as F naught, F c, these values they are being obtained from by conducting the experiment, and then Phillips equation is another equation. So, these are the some important equations which are being used to establish their constant, and then this is being used. So, in this particular lecture, dear participants, we have studied soil water constants and soil water potential. We studied soil water movement in relation to irrigation water application. We studied infiltration models. We also studied how to conduct infiltration test. We did study how to determine the hydraulic conductivity of the soil in the laboratory conditions. So, there are methods also to find out the hydraulic conductivity by using the field test. So, those are there. Now, in forthcoming lecture, we will work out some problems what we discussed in previous lectures, that is on fundamentals of fluid mechanics we studied. We also studied soil water movement as well as infiltration. So, we will work out in the coming lecture, we will do exercises, and so that you get hands on experience on these topics. So, you may refer these books. These are A. M. Michael by Irrigation and Theory and Practice, which can be used as a textbook, and then there are other books which can be used, and then these materials are available in e-course developed by us at at IIT Kharagpur for ICAR. So, such material can also be referred from there. Thank you very much.